Welcome students in the lecture series of some basic concepts of real analysis. In the previous lecture, we discussed that if f is continuous on a closed and bounded interval, then f has an absolute maximum on that closed and bounded interval I. Now, we are going to prove that if f is continuous on closed and bounded interval I, then f has also an absolute minimum on that closed and bounded interval I. So, let us start with the proof. Given that the function f is continuous on a closed and bounded interval I, this implies that minus f is also continuous on a closed and bounded interval I by the algebra of continuous functions. From above result, we can say that minus f has an absolute maximum on the closed and bounded interval I, which we discussed earlier in the previous lecture. That means we can say that if minus f has an absolute maximum on the interval I, then by the definition there must exist some element, say C star, belongs to the closed and bounded interval I, such that by the definition we can say that this inequality holds. That means minus f of x is less or equals to minus f of C star for all x belongs to the interval I, or in other words we can rewrite this inequality as minus f of x is less or equals to minus f of C star for all x belongs to the closed interval I. This implies that we get f of C star is less or equals to f of x for all x belongs to the closed and bounded interval I. Thus, from above inequality, we can say that the function f has an absolute minimum on the closed and bounded interval I. Hence, we conclude that if we have a continuous function f from I to R, where I is our closed and bounded interval, then if f is continuous on that interval, then the function f must have an absolute maximum and absolute minimum on the closed and bounded interval I. The geometrical interpretation for maximum and minimum theorem. The maximum minimum theorem for continuous functions on a closed interval means geometrically that a smooth unbroken curve drawn on a finite enclosed segment of the x-axis must have a highest peak, that means absolute maximum, and a lowest valley, that means absolute minimum within that segment, visually represented by the absolute highest and lowest y values the graph reaches before the stopping. These extrema occurs either at the end point of the intervals or at the flat spots, that means the critical points where the tangent line is horizontal, that means the derivative is 0. In other terms, imagine a perfectly drawn path on a short fenced-in road. Even if the path goes up and down, then the fence keeps it contained. Guaranteed, you will find the absolute highest spot and the absolute lowest spot on that specific stretch of road. Now, moving towards our next theorem. Our next theorem is location of roots theorem. The statement for the location of roots theorem is, let we have a closed and bounded interval I of the form I is equals to a comma b, and let consider a function f which is defined from I to R, which is continuous on the interval I, and given that if we have f of a is less or equals to 0 and 0 is strictly less than f of b, or if f of b is less than 0 and the 0 is less than f of a, that means f of a and f of b have opposite signs, then there exists a number c belongs to the open interval a comma b such that the value of the function f of c must be equals to 0. I repeat the definition of location of roots theorem for continuous functions. We have a closed and bounded interval I, and we define a function f from I to r which is continuous on the interval I. Given that if f of a and f of b have opposite signs, that means either f of a is less than 0 and 0 is less than f of b, or f of b is less than 0 and 0 is less than f of a. Then there must exist a number c belongs to the open interval a comma b such that f of c must be equals to 0. Let us start with a proof. Let us suppose f of a is strictly less than 0 and 0 is strictly less than f of b. Now consider the set capital S, and the capital set S defined as S is equals to x belongs to the closed and bounded interval a comma b with the condition that f of x is strictly less than 0. As we can see that the set S is non-empty because the point A must belong to the set S. Now let us recall the sign lemma. Sign lemma says that we have a function f from R to R which is a continuous at some point C in R, and let f of c is greater than 0. Then there exists a neighborhood V delta neighborhood of C such that if x belongs to that neighborhood, that implies f of x must be greater than 0. I repeat the sign lemma. Sign lemma says that if we have a continuous function f at some point c where the function define f from R to R with the condition that f of c is strictly greater than 0, then there exists a delta neighborhood of C such that if x belongs to that neighborhood, this implies f of x must be strictly greater than 0. Now, as considered the set S which is defined as S is equals to x belongs to the closed interval a comma b such that f of x is strictly less than 0. Then we can say that the set is non-empty because A belongs to the set S. As S is bounded above by the B, then by the completeness property of real numbers we can say that the set S must have a supremum say B. Now recall the completeness property of real number. The completeness property of real number says that every non-empty set of real numbers that has an upper bound also has a supremum in real numbers R. So from that we can say that the set S has a supremum in R, say that supremum is C. So we need to prove that there must exist some point C in the open interval a comma b such that f of c is equals to 0. Let us suppose if possible f of c is not equals to 0. So if f of c is not equals to 0, then we have following cases. First case is either f of c is strictly greater than 0, and the case 2 is or f of c is less than 0. So now consider case 1, that means the function f of c must be greater than 0. Using sign lemma, we can say that there exists a delta greater than 0 such that f of x must be greater than 0 for all x belongs to delta neighborhood of C intersection closed and bounded interval I. Say this is our equation number 1. I repeat the equation number 1. We are considering a case when f of c must be greater than 0. Then by sign lemma, we can say that there must exist some delta greater than 0 such that we have f of x is strictly greater than 0 for all x belongs to the delta neighborhood of C intersection the closed and bounded interval I. Now, as C is the supremum or least upper bound of the set S, then we can say that C minus delta cannot be an upper bound of the set S. This implies that if C minus delta is not an upper bound of S, then there must exist some point, say x1 belongs to the set S, such that we have our statement A. And the statement A says that x1 is strictly greater than C minus delta. Also, we have x1 belongs to the set S. This implies that we can say that x1 is less or equals to C, because C is the supremum, and for any delta C is strictly less than C plus delta. So, this is our statement B. So, from the statement A and statement B, we get C minus delta is strictly less than x1 and x1 is strictly less than C plus delta. That means x1 belongs to the open interval C minus delta comma C plus delta. That means we can say that x1 belongs to the delta neighborhood of C intersection I. This implies that f of x1 is strictly greater than 0, but we know that x1 belongs to S. If x1 belongs to S, then by the definition of a set S implies that f of x1 is strictly less than 0, because the set S is defined as x is equals to x belongs to the closed interval a comma b, such that f of x must be less than 0. So, by the definition of set S, we get f of x1 is strictly less than 0. This is contradiction to our assumptions, hence our assumptions are wrong, and we conclude that the following statement is false. That means f of C is strictly greater than 0. Now, consider the case 2. Case 2 is f of C is less than 0. Again, using sign lemma, if f of C is less than 0, then we can say that there must exist some delta greater than 0 by the sign lemma, such that we have f of x is less or equals to 0 for all x belongs to the delta neighborhood of C intersection I. This is our statement number 2. I repeat the statement number 2. We are considering the case when f of C is strictly less than 0. If f of C is strictly less than 0, then by the sign lemma we can say that there must exist a delta greater than 0, such that f of x is strictly less than 0, and the statement number 2 holds. And statement 2 says that f of x is strictly less than 0 for all x belongs to the delta neighborhood of C intersection I. That is, x belongs to the set S for all x belongs to the delta neighborhood of C intersection I. This implies that x is less or equals to C for all x belongs to the delta neighborhood of C intersection I. We can say that because the term C is a supremum of the set S. So, for any element x belongs to the set, then we can say that the every element of the set must be less or equals to the supremum C. That means we get x is less or equals to C for all x belongs to the delta neighborhood of C intersection I. This is a contradiction, as x belongs to the delta neighborhood of C intersection I. Hence, our assumptions are wrong, and we conclude that the following statement is false. That means f of C is strictly less than 0. Hence, our assumptions are wrong. What we take initially, that is f of C is not equals to 0. That means we get f of C must be equals to 0. Also, clearly C is not equals to A as well as C is not equals to B. That means C belongs to the open interval a comma b. Hence, we conclude that if we have a closed and bounded interval I defined as I is equals to a comma b, and a function f defined from I to R is continuous on that interval I, and we have f of a and f of b with opposite signs, that means f of a is strictly less than 0 and 0 is strictly less than f of b. In similar way, f of b is strictly less than 0 and 0 is strictly less than f of a. Then there must exist a number c belongs to the open interval a comma b such that f of c is equals to 0. Now, moving towards the geometrical interpretation, the geometrical interpretation of the location of roots theorem for continuous function is that if a continuous curve starts below the x axis, that means negative y values, at a point A and ends above the x axis, that means positive y values at the point B, it must cross the x axis at least once to get from one side to the other without lifting its pen on no brakes. This crossing point, whereas the function value is 0, is a root of the function, geometrically showing the graph intersect the x axis between A and B. In essence, the theorem guarantees that a sign changes in the continuous function over an intervals implies an x axis crossing, that means a root within that interval only. Now, moving towards our next theorem is Bolzano intermediate value theorem. The statement for Bolzano intermediate value theorem is, we have a interval I of the form closed interval a comma b and a function f which is defined from I to r, which is a continuous function on the interval I. And if we have a and b belongs to the interval I, and for any k belongs to the real number r which is satisfying, f of a is less or equals to k and f of b is strictly greater than k, then there exists a number c belongs to the interval I between a and b such that f of c must be equals to k. I repeat the statement for Bolzano intermediate value theorem. Bolzano intermediate value theorem states that if we have a interval I is equals to a comma b and a function f defined from I to r which is continuous on that interval I, if a and b belongs to the interval I with k be any real number satisfying the following inequality. The inequality says that f of a is strictly less than k and k is strictly less than f of b. Then there exists a number c belongs to the interval I which is defined as I is equals to close interval a comma b between a and b such that f of c must be equals to k. Now, let us start with the proof of Bolzano intermediate value theorem. As we know that I is a closed interval a comma b, that means a is not equals to c. So, let us assume a is strictly less than b. Then clearly we can say that the closed interval a comma b is contained in I. Now, define a function h as h of x is equals to f of x minus k from close interval a comma b to r. I repeat, we are defining a function h from close interval a comma b to r as h of x is equals to f of x minus k. As given in the statement, the function f of x is continuous on the interval I. This implies that the new function h of x is also continuous on the interval I by the algebra of continuous functions. Then we can say that the function h is continuous on the interval a comma b. Also, we have h of x is equals to f of x minus k. Then replace the values of a and b with respect to x, then we get h of a is equals to f of a minus k, and by the assumptions f of a minus k is less than 0 and h of b is equals to f of b minus k, which is again less than 0. Now, recall the statement of locations of roots theorem. The statement for location of root theorem is, if we have a closed and bounded interval I of the form I is equals to a comma b and a function f which is defined from I to R, which is a continuous on a closed and bounded interval I, and we have f of a is strictly less than 0 and 0 is strictly less than f of b, or f of b is strictly less than 0 or 0 is strictly less than f of a. That means f of a and f of b have opposite signs. Then there must exist a number c belongs to the interval a comma b, in fact belongs to the open interval a comma b, such that f of c is equals to 0. So, by location of roots theorem, there exists a number c belongs to the interval a comma b, or we can say that belongs to the open interval a comma b, such that h of c is equals to 0. That means f of c minus k is equals to 0, because our function h of x is defined as h of x is equals to f of x minus k. Then if we replace the value of c in place of x, we get h of c is equals to f of c minus k, and by the location of roots theorem we get h of c is equals to 0 for every c belongs to the open interval a comma b. Then from that we can say that f of c minus k is equals to 0. That implies from this we get f of c must be equals to k. Hence, we conclude that if I is an interval of the form a comma b and a function f defined from I to R is continuous on the interval I, if a and b belongs to the interval I and k be any real number R, satisfying f of a is less than k and k is strictly less than f of b, then there exists a number c belongs to the interval I between a and b, such that f of c is equals to k. Geometrical interpretation for the Bolzano's intermediate value theorem. Geometrically, the theorem for continuous function f on the closed interval a comma b means, if you draw a horizontal line y is equals to k between f of a and f of b, the graph of the function must cross that line at least once within the interval, showing that the function takes on every value between f of a and f of b without lifting your pen. Bolzano's theorem, a special case, states if f of a and f of b have opposite signs, that means one positive and one negative, the continuous graph must cross the x-axis, whereas f of c is equals to 0 somewhere between a and b, guaranteeing a root exists. Now, I repeat the statement of Bolzano's intermediate value theorem. The statement for Bolzano's intermediate value theorem is, if we have a interval I which is of the form closed interval which is equals to a comma b, and define a function f from I to R, which is a continuous function on the interval I, and we have a and b belongs to the interval I and k be any real number, satisfying the following inequality, and the inequality says that f of a is strictly less than k and k is strictly less than f of b. Then there exists a number c belongs to I between a and b such that f of c is equals to k. Now, in this lecture, we studied properties of a continuous functions, in which we studied boundedness theorem and their geometrical meaning. We studied maximum minimum theorem and their geometrical properties. We also discussed location of roots theorem and its geometrical pretension. We also discussed Bolzano intermediate value theorem and its geometrical interpretation. In the next lecture, we will discuss about its examples related to these theorems. Thank you.